In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. All right. So we are only slightly local here, so to speak. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the two routers. For your information, this could take millions of New Taiwan dollars. But installing a high-end server machines, it only takes this much New Taiwan dollars. So that's about 2 orders of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, all right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the client without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the request being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link. 60% of the scenario 1. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? the key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, pick, say, tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, all right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content, all right? And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2p file sharing. The idea of P2p file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Good. And you saw a bit already. Next slide. Coming next is going to be the second application in Chapter 2. And we'll look at how FTP defines its application layer protocol.